Have you ever just wished for a language that had absolutely zero ambiguity? You know, a way to say something so precisely that no one and no thing could ever misunderstand it? Well, that's exactly what we're diving into today, that quest for perfect clarity.
I mean, think about our everyday language, like English. It's fantastic, but man, is it messy. Take a word like reading. In one sentence, it's an action Alice is doing. In the next, it's a noun, a thing you have to do for homework. And in another, it's a place where Bob lives. Now, we get the difference from context, right? But for a computer, that ambiguity is a total disaster. It needs rules that are absolute, black and white.
So that leads us to the big question, doesn't it? How could we possibly build a language from the ground up that's perfectly precise? Well, the answer lies in an artificial language that was designed for this exact purpose: propositional logic. Now, you got to think of propositional logic less like a language you'd use to, order coffee in Paris, and more like a blueprint for pure thought. It's a formal language built for things like mathematics and computer science, where every single statement has one and only one crystal clear meaning. So what are the building blocks, the atoms of this language? They're called propositions. And a proposition is just a simple, declarative sentence that you can definitively label as either true or false. That's it. For example, the moon is made of green cheese. That's a proposition. It's false, obviously, but you can give it a truth value. But a question like, what time is it? Well, that's not a proposition because you can't answer it with true or false. Okay, so if propositions are the words, the nouns of our language, then what's the grammar? That's where logical connectives come in. These are these special operators we use to glue simple propositions together to build more complex, more interesting ideas. Let's meet the big three. First up, the simplest of them all, not. Its job is incredibly straightforward. It just takes a proposition and flips its truth value on its head. If a statement is true, putting not in front of it makes it false, and if it's false, not makes it true. Simple. And we can see this perfect precision in what's called a truth table. This little chart is our absolute source of truth. If our proposition, let's call it P, is true, then not P is false. If P is false, not P is true. Clean, simple, and absolutely zero room for misinterpretation. All right, now let's connect two propositions together with and. Think about this sentence. Alice likes cheese and Bob likes tomatoes. For that entire statement to be true, what has to happen? Well, both parts have to be true, right? If it turns out Alice actually hates cheese, the whole thing just falls apart. It's a lie. And the truth table for and shows you just how strict it is. Look at that last column. We only get a true in that one single scenario where both P and Q are true. If there's even a hint of falsehood in there, the whole expression becomes false. Okay, what about or? Now, this is where logic is a little different from how we talk every day. In logic, or is inclusive. All that means is that the statement P or Q is true if P is true, if Q is true, or even if they're both true. And its truth table shows you just how forgiving it is. It's basically the polar opposite of and. The statement is only false in that one single case where both P and Q are false. As long as there's at least one true anywhere in the mix, the whole thing is true. So we've got all these rules. How do we keep them straight? Well, that's what the truth table is for. It is the unambiguous rulebook for our language. It's the ultimate authority, the dictionary that tells us exactly what our connectives mean in every single possible situation. No guesswork, no kinda, no maybe. And building one might look a little intimidating, but it's really just a three-step recipe. First, you just count up how many different propositions you're working with. We'll call that N. Second, you figure out how many rows you need. And finally, you just fill in the columns for your variables using a really simple, clever alternating pattern. So how many rows do you need? The formula is dead simple, 2 to the power of n. So with two propositions, like P and Q, you need 2 squared, or 4 rows. If you had 3 propositions, you'd need 2 cubed, 8 rows. This little formula guarantees that we check every single possible combination of true and false every single time. Okay, now this is where things get really powerful. In this language of logic, it turns out that two statements that look completely different on the surface can actually mean the exact same thing. This is called logical equivalence, and we can prove it using our trusty truth tables. Let's put this to the test. Let's take this first expression, not P or Q. We build its truth table piece by piece. First, we figure out P or Q. Then, we just apply not to that whole column. We flip all the values. Now, look at that final column. Burn it into your memory. False, 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 true. Got it? Okay. Now let's look at a totally different looking statement. Not P and not Q. We build it up again. We find the not P column, the not Q column, and then we combine those with and. And what does that final column look like? False, 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 true. Whoa, wait a minute. The final columns are identical. This is our proof. This means that not P or Q is the exact same thing as saying not P and not Q. We've just proven one of De Morgan's laws, a super powerful tool that lets us find these secret synonyms and simplify really complex logical statements. Now, I know what you might be thinking. This is all very abstract, right? It feels like a philosopher's game. But this is the moment where we connect this pure, abstract language directly to the physical world, to the computer or the phone that you are watching this on right now. You see, our logical connectives, the and, the or, the not, they aren't just ideas on a page. They are physically built into microchips as things called logic gates. These are the microscopic switches that are the fundamental building blocks of every single digital circuit in existence. And here is the mind-blowing connection. Modern processors use components called lookup tables, or LUTs. And what is a lookup table? Get this, it is, for all intents and purposes, a physical hardware version of the truth tables we've been building. It's a tiny device that literally takes in electrical signals as inputs and spits out an output based on these exact pre-programmed rules of logic. And that is the whole journey. We started with these incredibly simple ideas of true and false. We used them to build a perfectly unambiguous language, and that language became the literal blueprint for the unbelievably complex digital machinery that powers our entire modern world. So think about that. The next time you're writing code, or even just tapping on your phone screen, remember what's happening deep down inside. Beneath all the beautiful interfaces and complex software, at the most fundamental level of reality, it's all just executing the simple, powerful, and perfectly clear rules of propositional logic. It all boils down to an intricate dance of true or false.